Okay, ready to start? Here we go. So so our next exam is a week from today. Exam 3 is a week from today. So in exam prep, I've started to build your resources here for exam 3. Some of you will say, how can I do better in this class? So one big way is to get started studying early, like start this weekend, start studying for the exam. So I've got an outline of 4 things, and this will continue to be supplemented, but I've got a concept and skills outline. So this is just like kind of bullet points. Know what this is, know what this means, know how to do this. Okay, so that's really important. That's kind of like the centerpiece of your studying. There won't be anything on the exam that's not highlighted in this little sheet here, this outline. Okay, and then I've got 2 sheets of practice problems, practice A, practice B. Here's the cover page, or on the cover page will be this. So you will finish this drawing and write out what the coordinates X, Y, and Z are in cylindrical and spherical coordinates for a bonus point, and then you'll have it as a reference for the test. Okay? So you should be able to do that as it is, but rather than trying to think of those things on the fly, before you start the exam, label everything in the picture and fill out the table. I'll also give you these things. So you can check that out. Versions of dA, versions of dV, volume of a sphere, volume of a cone. So that's there. So you know exactly what's on the cover page. And then all the web work is great practice for studying. We started doing these written homeworks and recitation every week. Those are written by me. Okay, so those are great for studying. More practice. You won't remember. Just do them again. Okay, just work them again. Practice problems up here, and then I'll make a list of book exercises. Should be a little more like drill and practice type things. But you always, whenever you're studying and working the problems, you've got to get out of the mindset of what do I do to get the right answer, and get into the mindset of what are the concepts and things I need to understand in this problem that I could transfer to something new, right? So there will be questions on the exam that will use principles that we've learned but might not be anything you've seen before. Okay, you need to be able to succeed at those. So that means extending the important principles and concepts of the problems that you've done into something new. Adam? Yeah, it'll be the chapter reviews. Yeah, so whatever, just email me. If you can't find what you need, just email me. Yeah, so if it's not enough, whatever I do, if it's not enough, then email me. Other questions about exam 3? So, how do you do better? You get started studying early. You can't start studying for this test on Tuesday. It's definitely not on Wednesday. Okay? You've got to start early. And so why? So that you can figure out what you are good at and what you understand and what you don't, and then you come and you have conversations with me, or conversations with Key, or conversations with each other. That's where your score is gonna jump the greatest, is through conversations about the principles, about the understanding stuff. Okay? So get into office hours next week with your questions based on your studying this weekend. Yes, please.
When is the last day of like the stuff that might be on the test?
Today.
Today, okay.
Yep. So stuff today is fair game, but next week is not.
Are you going to do the web work again, where like next week's web work won't be due until like Friday?
Sure. Definitely. Other questions? Okay, so I wanted to talk about one question. On your last written homework, there were a couple solids on the front page that you had to do both in cylindrical and spherical coordinates. Do you remember this? And the second one, like number 1B, looked like this. it was, I think it was what? Outside of the cone and inside the sphere? Is it like that? So you had a sphere. Like that. And then did you have a cone? And so you had an intersection like this. And you were doing outside of the cone and inside of the sphere. Is that right? And you had one thing you had to do was you had to write a triple integral in cylindrical coordinates. And when I glanced through the first 10 or 12 people, it looked like there was very little thought put into that. It was just kind of write down the things quickly. But what is our for cylindrical coordinates? What's the general scheme of a triple integral in cylindrical coordinates? What's the scheme? What do we think about? So we have a function, right? And then it's going to end up being an r and theta, right? R dz dr d theta. So as we're building these limits of integration, what's our scheme, or how do we think about this? What do we think about first? Z. So when you say dz, what's our little phrase? We're going to say what? Bottom to top surface. And when you have this thing, bottom to top, what's the bottom? Z equals 0. And what's the top? So we're talking about now this stuff in here, right? We're talking about all this stuff around here. What's the top of this? A ring? For small values of x and y, the top is the cone. For larger values, or small values of r, the top is the cone. For larger values of r, the top is the sphere. Do you see that? So yeah, so this is, you have to sum it up, right? You're going to sum it up, and your dividing point is going to be whatever r value you get at that intersection, right? So there's going to be an r value like this. And when you're inside that r value, the top of this solid is the cone. When r is greater than that boundary, the top of it is the sphere. So with like a majority of the people, as I ruffled through, it looked like there was really no work done, and you just kind of wrote some stuff down. 0, square root of 45, blah, blah. You just kind of, it was like there was really no thought about this. But cylindrical coordinates means bottom surface to top surface first, dz, right? And in this case, you've got a split top, right? You have a split top. When r is small, the top is the cone. When r is big, the top is the sphere. Okay, does it make sense? So you got to be thoughtful. You have to go slow, really conceive the solid, and then go slow. You know, bottom. What's the bottom? Is it the same everywhere? Okay. What's the top? Is it the same everywhere? Oh no, it's not the same. Part of it is the cone. Part of it's the sphere. So I got to split this up into two triple integrals according to r, right? So these r limits are going to govern what the top is, right? So when r goes from 0 to whatever that r value is, called r naught, then the top's going to be the cone. And then when r goes from that r1 out to the greatest r here, you're going to go from 0 to the sphere for dz. Does it make sense? Okay, so lots of practice of triple and double integrals to get ready for the exam. Okay, so let's start. So we've been talking about vector fields, and then you guys worked on gradient fields. Sorry that one problem was all or nothing for credit. So that's kind of out of my control. But the person who coded the one problem where you had the four surfaces that you could rotate, and you had to figure out which gradient fields matched, you had to get all 4 to get credit. If you missed one, you got 0%. That's the way they coded it. Sorry about that. So I'm sure many of you that didn't get it got 2 and 3 of those correct. Okay, and you can see the answers now. So it's a really good problem, but unfortunately they made it all or nothing. All right, so now we're going to talk about line integrals. So there's two kinds of line integrals, okay? So first type is line integrals of multivariable functions, right? Multivariable, real valued multivariable function, right? So a multivariable means there's two input variables, and we get a real value for every ordered pair, x, y. We get a real value. Okay, so we can think of these, and then these look like this. So it's a single integral of our function ds over some curve C. That's an S. It's still an S. I'm trying to draw it too slow. Okay, there we go. So we got to make sense of all this. So this can have meaning in terms of rate of change and accumulation, or it can have meaning in terms of geometry. Okay, so let's do the geometry first. Geometry, the meaning in terms of geometry, and how do we represent graphically f of x, y? How does that represent it? What's that? But how is it represented visually, graphically? F of x, y? A surface, right? A surface. We let z be that dependent variable. So our independent is ordered pairs in the xy plane, and given an ordered pair, the function tells us the z value, and then all those z values make a surface, right? Okay, so this is f. And then what is C? So C is a curve or a path, right? It's a path or a curve or a line or a circle. So some kind of path in the xy plane, so something like this. It has a starting and an ending point. So what do we want to do? So we're going to accumulate this surface fxy only over the ordered pairs on the path C. Okay, so what would that be like? So we only care about the part of this surface that is defined by these ordered pairs. So for instance, at the starting point here, so we could say it's oriented this way. So at the starting point here, say it's that. And then we only care about the z values for the ordered pairs of the path. This is going to be like this, something like this. It's going to be on the surface. It's going to be the points of the surface only for the ordered pairs on the path. Okay, so if we're going to integrate or accumulate the surface F only for points over that path, what would the geometric interpretation be? What do you think? So I'm going to integrate across here over this path C. What's that?
Surface or curved plane.
And what is that like?
It's a cylinder. So the intersection between the C cylinder and the F cylinder.
Okay, so are you imagining a vertical, something vertical, right?
Yeah.
Vertical with this shape, that's right. And then the height of it can vary according to Z, right?
Yeah. So it's the intersection.
And what about that? So we kind of it's like a curtain. Yeah. Surface area of the curtain. Okay? So as this thing is, so it's kind of wavy like this, right? It's like a, not my finest artistic moment. But it's like a curtain, right? It's like a curtain. It's wavy according to C. It's wavy according to C, and then its height varies according to the surface, Z. Right, so the height would be, the height of it is on the surface, so that can vary up and down, and then it can be wavy according to C. And so then what would we get? We'd get the area. So will we always get an area for a line integral if we think about what's analogous to what we've learned in the past? Will it always be area? Do integrals always give area? No, what do they give? No. We're talking about geometry now. Geometry. Do they always give? Do single integrals always give area under the curve? They do not. What do they give? No, we're talking about geometry, not accumulation. We're talking about geometry. Yeah. Nope. Just a basic integral. Does not give area, guys. What does it give? Thank you, Mark. What is it? Difference of areas. Why is it difference of areas? If what? What about F? What's that? No, well, no, that's not, that's different. So, okay, so you were thinking F of A, F of B minus F of A. You kind of got lucky there, all right? So that's a different difference. Okay, so yeah, so that it's the net change, the net change of our antiderivative. But in terms of geometry, what happens to F if it goes underneath? What happens to this area? It gets subtracted, right? It gets subtracted. So integrals get a net accumulation or net change. So if we go from A to B here, we're going to get this area minus this area. It's not going to be total area. It's going to be the difference of areas. Same thing with a line integral. If that surface ever dips below the xy plane, where C is going, right, over the path C, then you're going to get a difference, right? Any part of that curtain that's now below the xy plane, that area gets subtracted, has a negative contribution to the integral. Just like this situation here in Calc 1. Okay, so it's going to be net area between the surface and the xy plane. Should be typing. Is the net area between the surface of F and the xy plane for ordered pairs along the path C. This is geometric interpretation, right? Okay, so then in terms of rate of change and accumulation now, not geometry, what would be represented by our function f? So if we're doing a rate, accumulation, interpretation, what would the function f represent? What would the function f be if we're looking at a line integral like this in terms of a rate and accumulation interpretation? It'd be the rate of change function, right? It'd be the rate of change function for something of two variables. Okay, so some rate of change with respect to two different variables. And then what would the whole integral be? Net accumulation for ordered pairs x and y on C, right? So for wherever ordered pairs are on the path of C, we'd be accumulating at the rate of f, right? Yeah. Net accumulation for ordered pairs along the path of C. Given rate of change of f. Okay, so we'll do an example of each of those. But first, we got more to talk about before we got to examples. So, how do we express C? How do we express C? So, because so in this class, how would we learn to express curves like that? Using what kind of thing? Yeah. No, we're just talking about a curve now. So cylinder is a surface. I'm just talking about a curve. Right. So both in terms of parameter is called what? If we find a curve where each coordinate is in terms of parameter, what kind of thing is that? Vector function, right? So C is going to be described as our vector function R in terms of some parameter T. So we could say like G of T is X and H of T is Y. And we'd have a vector function, right? Okay, so now what is ds? ds, if you remember from Calc 2, ds is a little bit of length of the curve of C. So it's a little length of the curve C. So what would ds dt be? Because we're gonna need to evaluate this integral, and when we evaluate this integral, if our curve is defined as this vector function with respect to t, then we want to solve that integral with respect to t. So we need to get this whole integral in terms of t, our parameter for the curve. So ds is the length of the curve C. So what would ds dt be then? What would ds dt be? Right. So it would be a rate of change, right? It would be. So how could we say? So for amount of curve swept out. Sorry. So for amount of change in t. So for an amount of change in t. How much length you would get, right? So this is the rate of change of length of C for change in T. So how can I write ds dt in terms of the vector function r? So remembering about vector functions. Vector functions, what? They sweep out curves in the plane, in this case, or curves in space. So what would ds dt be in terms of the function r? ds dt is given a change in t, how much length of curve you get of c, right? So if that's a big number, then a little change in t sweeps out a lot of the curve, right? And if ds dt is a small number, then a little change in t only gives you a little bit of the curve. So what is that kind of like? What is that? Yeah, what's it? Okay, so velocity is the vector. Is ds dt a vector? Speed, right? Like, isn't this like speed? If t is time, magnitude of what? Okay, so what would that be? So how would we express that in terms of r? So ds dt would be the same as magnitude of r prime of t. Does it make sense? How much arc length we get for a change in t would be like the derivative function, right? But just the magnitude of it. We don't care about the direction. Does it make sense? That should make sense with it. So you have to think back like a month now, right? When we did all that stuff with position, velocity, and acceleration, and we're working with those vector functions. I think that was exam one. It was exam one. I told you it's all coming back. Everything comes back. All right, so this allows us to write what ds is in terms of t. What is ds then? ds is magnitude of r prime times dt. So that's what we're going to put in to rewrite this thing in terms of t. And then we're just going to rewrite our function, right? Everywhere there's an x, we're going to have what? G of t. And everywhere there's a y, h of t. And that will get our whole integral in terms of t. Does that make sense? And then we're going to solve that thing in terms of t. Okay, so questions so far? So then this thing will become, we're going to integrate from the starting value of t to the ending value of t. We're going to integrate f of what? G of t, h of t. And our ds is going to be magnitude of RT dt. Can I move move on to a blank screen. Are we good? Anybody have a question? Okay. So let's do this one. We're going to do integral. So example. Okay, so what's our function? X. Is that a function of x and y? Mark says yes. Is it a function of x and y? Sure. Is y equals 3 a function of x? Sure. Right? Given any x, the y is 3. Right? So just it's a function of x. So our function of x and y is x. So what do we need to do? We need to get our vector function for this thing, right? So C is going to be, we need to get our vector function for this thing. So let's sketch it. It's easy sketch. From -1, 1, 2, 3, 9. And we need to write this curve, y equals x squared, as a vector function. We've done it, but it was a long time ago. So how do I write x as a function of t and y as a function of t so that it's equivalent to y equals x squared? Anybody remember what we can do? Yeah? Okay, and what would be the more strategic way to go here? T for x. So y is t squared. So this is one particular technique for writing a vector function from a curve, from an equation of x and y. Do you do it for all of them? No. For instance, circles. Not going to use that for circles. Okay? Circles is a different technique. Or ellipses. Okay? But if you have like polynomial curves like this is a good way to go. Don't do this for a circle, because then you end up using it gets ugly. So we want a different way to parameterize a circle. And again, that was back in the first couple weeks of class. We did that. All right, so we got our vector function. So therefore, what is f in terms of t? So f of what t and t squared would be? Because x is t now, right? And y is t squared? T. And what is our ds? ds equals magnitude of r prime of t dt. So what's r prime of t? 1 and 2t. Magnitude is 1 + 4t squared, square root. So now we're ready to go. So our integral equals, we're going to do the integral of x is t, ds is square root of 1 plus 4t squared dt. And what does t vary from? Because t is our x coordinate, to vary from this ordered pair to this ordered pair, our t is going to vary also, just like the x, from -1 to 3. That's only because of the fact that our x coordinate is t, right? Okay, this is a pretty straightforward antiderivative. You notice this is the result of what derivative rule? Question?
Yeah, if x wasn't t,
Right.
then how would we figure out the value?
So we need the t value that gives us that ordered pair according to our vector function, right? So we're going to use, there's a t associated with that ordered pair, a t that gives you -1, 1 in your vector function, and that's the t you want there. And then the t that gives you that ordered pair there is your final t. Okay, this is, if we think of this as a derivative, it's what kind of derivative? Chain rule, right? This is the derivative of the inside, right? Essentially, because this is 4t squared, t to the first is essentially the derivative of that inside, right? So if you think about doing the chain rule, you do the chain rule, you multiply by the derivative of the inside, which is something t to the first. So antiderivative would mean this would collapse back inside, and we'd leave the inside as it is, and it would be to what power? 3/2, right? Because this is the 1/2 power. Now we got to clean up the mess, right? There's going to be a 2/3.
And there's also a
1/8, right? Because when you take the derivative, you're going to get 8t. We don't have the 8. So we need 1/8. I think that does it. The 2/3 takes care of the 3/2 on the derivative, and the 1/8 takes care of the 8 when you have the 8t. But then now the derivative of this will be exactly what we started with, and we're going to evaluate that now from -1 to 3. And we won't take the time to do that. Piece of cake from there, right? And you actually get something close to 18. It's about 17.8. So that would either be the net. Let's see. Let's graph it. See what we get. So we want to graph z equals x, and we want to graph the curve is y equals x squared, right? And we want to look at some lighter colors here. There we go. Can I erase the writing? Did you guys get everything written down? Okay, so what's the meaning of this? From x equals -1. There we go. So this is the y-axis coming out at us here. Right now the x-axis is to the left. So x equals -1. The z value would be, oh, here, right? So this is x equals -1 here, right? So positive x is to the left, so -1 is this way. And then up to, is that dark? I bet that's dark. No, red's worse. Both gray. Gray is the lightest I got. Okay, that's not bad. I'll do red on here. So this -1, x equals -1, 2. Does that show up? Good. Okay, cool. So it's like that. All right, and it's but actually then below, right? So below, so the z is positive here. So this is the positive contribution to that whole integral. But then z is negative over here. So that's all below, right? So this is all z is positive, so you get all positive contribution of that area, and then you have a negative contribution of that little area there. So had we gone from 0 to 3, we would have gotten a larger value. Okay, questions on that? All right, so let's do this one. So we have another example. We have a roof of a building. Is z equals 10 minus 1/8 x squared minus 1/12 y squared. Yes. So what kind of shape roof is that? We have linear z and quadratics x and y of the same negative paraboloid, right? That's a paraboloid. So paraboloidic roof, and there's going to be a wall along this side here. 2x plus y equals 8. From the floor to the roof, along, what did I just say? 2x plus y equals 8. And we want to find the area of the wall. In the first quadrant, or first octant. So the wall, so the river line in the first quadrant. Find the area of the wall from the floor to the roof.
X squared, what is that number?
1/8. The coefficient? 1/8. Yeah. Sorry. Okay, so we're going to do an integral here. So what will define f and what will define our c? So f is, he's saying z, he's saying the roof, right? That's the surface, right? So f is going to be our 10 minus 1/8 x squared minus 1/12 y squared. Okay, and then what's going to be our c? Yeah, so we're gonna integrate that surface over this path, right? The path in the first quadrant. So r of t is going to be according to, so 2x plus y equals 8. What is the x-intercept? What makes y 0? 4. What's the y-intercept? 8 will make x equal to 0. And what kind of path is it? Linear path. Okay. So with a linear segment, so there's different ways we can go here, but we could do, so let's make this t equals 0 and this t equals 1 and figure out how we would parameterize that segment so that this would be our starting point, 0, 8, and our ending point would be 4, 0. Now I have a, so, and let's look at the picture. I have a pretty picture of this here. Where is it? No, it's here. So can you see that? So what are we finding the area of? So this is the roof is the gold, right? And the wall is kind of purplish. And so here's the floor, here's this wall. And the top of it is according to the surface, that paraboloid. So that cuts diagonally through space, right? It cuts diagonally across the x and the y-axis. So we're finding that, and it's truly an area. Why? Because the surface is always positive, right? Z is always positive over that path. So then this truly finds an area, not a difference of areas. Right, so yeah, so here's our 4 here. This is x equals 4, y equals 8. Okay, makes sense? All right, so now we need to parameterize this line, right? So at t equals 0, we want to get the point what? 0, 8, right? So we want to get 0, 8 when t equals 0. So that's going to be our kind of like our so we just got to figure out then, so when we plug 0 in for t, we just want to leave 0, 8. So it's going to be 0 plus something t and 8 plus something t. Does that make sense? So then when we plug 1 in for t, we want to get the point what? 4, 0, right? 4, 0. So when I plug 1 in for t, I want to get 4 here. So what should that coefficient be? 4. And when I plug 1 in for t, I want to get 0. So what should this coefficient be? Negative 8. So we got it. 0 plus 4t, 8 plus negative 8t. So this is your starting, so this is how you parameterize a segment. Your starting point is this. On the segment for t equals 0. And then what does the 4 represent? 4 represents what? Final x minus initial x, right? And what does the 8 represent? Final y minus initial y. So that's final x minus initial x. And that's how you can do the parameterize a segment so that the starting point. So this is it's just convenient for the limits of integration, right? So that it'll be 0 to 1. Okay, so now we're ready to write the integral. It'll be the integral from. Limits will be.
0 to
Right, 0 to 1. That's why we did it the way we did it. So we could easily just write 0 to 1. of f, but so we know f is our this, but it needs to be in terms of t. So it's going to be 10 minus 1/8 times 4t quantity squared minus 1/12, 8 minus 8t quantity squared. And we got more work to do, right? Because now we need ds, which is the magnitude of r prime of t. So we need to get r prime of t. R prime of t is 4 negative 8. Magnitude of that is 1664, 80, radical 80. So that's our r prime of t, right? So for a change in t, we get what? A constant change in length, because it's linear. It's a linear path. A linear path with the way that we parameterized it for a constant, for the same change in t, you're always going to get the same change in length. That's why this is just a number, right? So radical 80 times dt. So what we got a bunch of, we're going to expand, and then it's an easy antiderivative. It's just a polynomial, right? So I'm not going to do that. So expand out, do all the algebra. And then term by term, antiderivative. Gather like terms, and then do the math. Antiderivative of polynomial is easy. Questions on that example? And so what is that finding then? In the end, it finds the area of this wall, whose top is the roof, the curved roof, and it's along this path C from 0, 8 to 4, 0. Questions? So that was positive x, and that's positive y. Okay, so then there's, that's the first kind of line integrals, right? So line integrals of just a function of x and y. So then the next kind of line integral is line integrals of vector fields. So let's talk about what that's about. Last chance for questions for this. So line integrals of multivariable real valued function, and then we have line integrals of vector fields. So what do those look like? We're still in a path. But so before I write what it is, let's talk about. So a very common application of this is work. So if this is a force field, okay, so oftentimes we think about these line integrals of vector fields as force fields, meaning at any point the vector field tells you what the force is, and we know force is a vector because force has magnitude and direction, right? So for instance, here at 1, 1, what can you tell me about the force here at 1, 1? So this force field is pushing whatever in it, right? Pushing whatever in it. In which direction? Just basically all in the x direction and not in the y direction at all. Okay? What about at 6-1? How does the amount of push compare to at 1-1? Greater push, right? Because it's a larger vector. And a different direction. Now we've got some y involved too, right? So it's to the right also, but now a little bit up also. All right, so that's the idea of a force field, that depending on your location, you experience a different force, which has direction and magnitude. Okay, so if I were to move through this force field, say like in a path like this, so we have forces applied over this distance, c. So what does the vector field do? If it's applying force to, say, a particle moving through it, that means the force field does work, right? It does work on things that move in it, right? It does work on things that move in it. And what work was our, right? Force times distance. But this is very complicated, right? It's not just, there isn't just a number for the force and a distance that we go, right? Because what about the force here? It's totally varying, right? And then what about the distance? Well, the distance is according to some path here. So we need to break it up a little bit. Okay? So say right here, we think about a little change in distance. And so our, what? So this vector is representative of what? It's representative of the direction that the curve is going at that moment. So what would that be? If C is defined as RT, so if C is defined as RT, then what's that vector right there showing the direction that, right, so that's going to be R prime of T. Now, which direction is the force right there? Well, the force is kind of like, I'll do that in blue, the force is kind of like this. Right? I'm looking at the one to the left and I'm just putting its tail there on the thing. Okay, so how much work is the force field going to be doing on the particle as it's moving in the direction of the red vector if the force vector is that way? So what we want, is it going to do the amount of work corresponding to all this force? No. So how much work is it going to do according to what force? Yes, sir. In the back. Oh, I like to hear what he said. In as much as it's going in the same direction as the particle. So we want the amount of force in as much as the same direction of that. What is that? Oh, good. You're smart. Good. You remember. We want this, so if it's only going to be about this much of that force. That's supposed to be a little arrow, parallel to the red one. That's the parallel component. The component of the red one, component of the blue one in the direction of the red one. So only that much of the force is going to apply in terms of what the work that the force field does. So what do we need? We need a little bit of work is going to be That's an r prime, right? So it's going to be the force, what? Dot. So if it's a little bit of rate of change, then we can say dr. So r prime of t, right, is like the direction and magnitude. And so now we're saying we want just a little, just representing a tiny change in t. And so that would be then dr. Right? So then our line integral would be over the path of force dot dr, and that dot product gives us only, for each little part, it gives us just the component of the force in the direction of the curve, which is our derivative, right? Derivative of the vector function. And then we're going to write this in terms of t. So our vector field will be, so we'll have t1 to t2. Our vector field will be, again, f of t. Oh wait, so f is ordered pair. So we'll see it come out in an example. I don't want to try to write this here. But dr is going to be dx and dy, and those are each going to be in terms of t. So it's dx dt, dy dt. And then times dt. So we'll write our force field, which will be in terms of x and y, which will change in terms of x and t, and then dr will be dx dt, dy dt, and then dt. So this particular one that I've drawn here, is that going to be a positive, zero, or negative amount of work? What do you think? Why positive? So if you think about accumulating the components of the forces in the direction of c, is there going to be an overall accumulation of positive force or negative force? Positive, right? Okay, how about a new path like this? I'm going to go from here to here. I hear negative and I hear zero. And by zero, we mean close to zero.
Oh, yeah, close to zero.
So do you see that the components of these forces in the direction, there's virtually zero force in the direction of, so we'll call this C2. There's, all along C2, if you take the component of the force in the direction of the path, essentially, there's zero force. So zero work. Okay, so what if we did do something else here?
That's definitely negative.
So if C3 goes from this point to this point, then the vector field will do what kind of work on this one? But the overall, so the overall value of the work is just going to be a number in the end. So that work will certainly be negative because you have all this accumulation of negative work here, and then there's a little bit of positive accumulation, positive contribution, but nothing that would overtake how much negative work was done at the beginning. So if we did the integral of the vector field for C3, we'd expect a negative value. For C2, something really close to zero, and for C1, something positive. let's do them. Here we go. All right. Can we do an example? Let's do an example. Here we go. Okay. So let's find where F is our vector field, x, y, and 1 minus x. And C is part of the circle of radius 2, centered at the origin. From (2, 0) to (-2, 0). And so before we actually do all the math, let's predict if it's going to be positive or negative. So let's pull that vector. Let's sketch that vector field and the path and see what we think for the. So for the vector field, is what? X, y, 1 minus x. Zoom in here. Okay, and then I want the circle. So let's as I graph this, let's think about parameterizing this, right? So I want the circle. How do I parameterize a circle with center at the origin? This is back from week 2, right? Week 2 of the class, back in August, early September. We talked about parameterizing circles, or writing a vector function for a circle. We don't want to make xt. So we want to use cosine and sine. So we want a circle radius 2 centered at the origin. So my x coordinate will be 2 cosine t. And my y will be 2 sine t. And I want t to go from what to what?
Because we're starting from 2.
I'm going to start from 2, 0 and go to -2, 0. So my t is my angle measure, right? 0 to pi, right? Let's predict. So based on the direction and magnitudes of these vectors, I'm gonna go counterclockwise around from 2, 0 to -2, 0. What do you think? Are we gonna get 0, positive, or negative value here?
Negative.
So here we're accumulating large positive or 0, or sorry, large or small, positive or negative, or 0?
Small negative.
Small negative, right? So we get a small negative accumulation. What about through here?
0. You're getting close.
So the vectors are pointed this way. So through here, not much, right? Maybe a teeny bit positive, but mostly 0. And then what about down here? Large negative contribution. So small negative, then small positive, mostly 0 through here, and then a large negative. So we expect this to be in the end? Negative. Okay, so we're expecting a negative amount of work. All right, so we've got our parameterization. So here we go. So, and we're going to integrate from, what did we say?
0 to pi.
0 to pi. And it's going to be xy 1 minus x. So xy will be
2 cosine t, 2 sine t.
2 cosine t times 2 sine t, comma, is it 1 minus x? So 1 minus, I'm going to write c for cosine. Okay, so that's 2 cosine t, dot, right, dr, right? So here's our r, 2 cosine t, 2 sine t. So what's dr? So negative 2 sine t, comma, 2 cosine t, dt. Dot product gives work because it only takes the part of the force so much as in the direction that we're going, right? So this is like the direction that it goes all the time, right? That dr is showing direction for a change in t. It's showing direction that you go, negative 2 sine t, 2 cosine t. And so we're only going to, by dot product with a force, we just gather up all the force in as much as it's in the direction of this for any t, right? Okay, so then we get equals, a little bit of ugliness here. So how do we do dot product? So this will be 8, negative 8 sine squared cosine. Is that right? Negative 8 sine squared t cosine t. Then what? Plus. So, right, so dot product is just product of the corresponding components, add them together. So this will be 2 cosine t minus 4 cosine squared t. Check my math. dt. Okay, let's talk about each of these antiderivatives. This one. Look at, I have sine t squared, and then I have cosine t. That's what kind of derivative? That's chain rule, right? So it would be negative 8. So in the chain rule, the derivative of the inside pops out. Here it is, cosine t. So it'll be sine t to what power? Cubed over, and we'll need 1/3. Did you catch it? Negative 8 over 3 sine. If you're not sure, then just take the derivative of this, and you'll get exactly this. And that'll help you to see how we got that. All right, derivative of 2 cosine t is, or antiderivative, sorry. Just 2 sine t, right? And then 4 cosine squared t. Anybody remember from Calc 2 how you do either just plain cosine squared or sine squared? How do you do that antiderivative? It's called the half angle identity. The half angle identity. Cosine squared is 1/2. I don't even remember it. 1 minus cosine 2t or 1 plus cosine 2t? 1/2 1 plus cosine 2t for cosine squared. So it'll be minus 4 times that. That's how you, and then that's how you solve, do the antiderivative for just cosine squared or just sine squared. We're not going to finish. And then, so then you've got your antiderivative, and you're evaluating from 0 to pi. And so, unfortunately, we couldn't see that turns out to be a negative value, right? That's going to be negative, as we predicted from looking at the path and the vector field.
Well, you can see that because you only got 2 sine